Let's take a look at another important feature of Linux systems, Red Hat Enterprise being no exception, and that is checksums. We'll label this section checksums. Why are checksums important? Because they provide us with a means of generating a unique signature per file, which can be cross-referenced by anyone with an equivalent checksum utility. So it's a question of integrity as opposed to confidentiality, which is provided with encryption services. So features include integrity checks on content or files. And of course, this can be extended to applications like email, for example. Now, there are a number of tools included. So, included tools include traditional MD5 sum, which is 128-bit based and generates the weakest of the four that we'll look at, but nonetheless is still in wide usage and is considered to be secure enough for common configurations. SHA-1 sum, which is based on the SHA-1 spec, which is 160-bit, which many firewalls use for VPNs. There's also SHA-224, but we'll skip over that and just move straight to SHA-256, which doubles our MD5 sum efforts. And SHA-512. So SHA seems to have won the battle with respect to the summing technology, checksumming technology that is going to be leading us into the future. So the notion is you have data that you'd like to share, perhaps via CDs, DVDs, optical drives, USB pen sticks, email, the internet, so on and so forth. For any bit of information that you generate that you'd like to share, it helps if you also generate a checksum. This will help you, for example, if you're transferring data across the internet, across wide area network connections where you're subject to, let's say, packet loss and data corruption. Even a bit makes a difference, let alone a full byte. So if you generate sums for your content and force your business partners to confirm those sums, then there should be little to no room for errors, and as a consequence, the integrity of your data will be much, much greater. So let's define some tasks, and that is to explore each tool, beginning with MD5 sum. Now let's see where MD5 sum is located on the system. We'll do a which MD5 sum. It's in user bin. To find out which package is responsible for it, we'll use RPM query file, user bin MD5 sum. This will tell us its membership and that it is a member of the core utilities package, as are the other summing technologies. So summing or checksumming is considered to be a core utility, regardless of which is used, which algorithm is used. So MD5 sum is in the path and can be used to generate sums on content. Now let's find some content that's worth summing. Let's navigate to our home directory. So here we've got a bunch of files named 1million.txt something or the other. So we can pick a single file like 1million.txt and sum it using MD5 sum. This will generate, to stand it out, a unique sum that corresponds to the contents of 1million.txt, such that when 1million.txt is transferred to a business partner, they can use their summing application, which supports MD5, to confirm that the sum begins with 8A, as we see to the left, and terminates with 582. And if that is the case, then that guarantees us that the file has not changed in transit. And in transit could mean within your local area network, perhaps from your server to the backup server, or from your server to the email server, or to the web server, or through the content switch, or what have you. So this tells us that the sum of 1million.txt is this particular string. Let's MD5 sum a different file. Let's try 1million.txt2, since the content's identical. Notice that although the file name is different, because the content are identical, the sum is still the same. So let's just note it, that MD5 sum against 1million.txt returns string that is unique to its content. And similarly, when we md5 sum 1,000,000.text2 returns the same string because the content are identical, which is something to note because it doesn't necessarily matter from the perspective of the summing technology, the name of the file, but more so the content of the file. So it's really what's inside that matters. So either of these that we query will return the same string. Let's try 3, 4, and 5. So long as the content is the same, then the string will be the same. Now to prove it, we can vary the content of one of these files. Let's copy 1,000,000.text to 1,000,000.text6, and then let's use echo to change it. We could have changed one of the existing ones, but as opposed to doing that, we just figured let's copy it. We have the storage and it's quick enough. Let's echo 1,000,001, which will be a new record that is a part of this particular item. So this is 1,000,000, this will be 1,000,001 into 1,000,000.text6. So now when we look at the 1,000,000 files, the text6 file will be slightly bigger than the others. Let's go ahead and try to md5 sum 1,000,000 texts and then 1,000,000 text6 to see if there are differences. Notice that it's an entirely different string with just one line of difference. So the summing technology significantly differs the string that's returned, which is why this is so important to be used and should be in more widespread usage, because it truly uniquely identifies the content of your documents, even if you change it by a single bit. For example, if we were to modify 1,000,000.text5, for example, and just add a single space, let's say, or a space at the end of the first line, which would be unbeknownst unless you're using some special editor that's able to pair in and show you where the spaces are, which there's certainly plenty of them within Linux, we'd figure that the files are the same. Now let's take a look and compare and contrast 1,000,000.text to 1,000,000.text5, and notice text5 has now changed considerably, whereas before it was the following string. So introducing a single space makes all the difference in the world. Let's just note, or as task C, alter content in various files and compare md5 sums. Note a single bit differential will cause the checksum to vary, which means there's a difference, which means if you have transferred information across the net or via email and the recipient registers a slightly different or considerably different checksum, then you know the content have been changed during transit, which is not a good thing. Now let's look at SHA-1 sum, which is used for 160-bit algorithm-based checksumming. So you'll see a lot of content on the net that's available with a SHA-1 sum. The execution is almost identical, with the exception being you're referencing SHA-1 sum as opposed to MD5 sum. So SHA-1 sum against 1,000,000.text will give us a 160-bit length unique string. The larger the bit length, the more strings, the more values we have to play with. Before we clear screen, let's just compare it. You'll see that SHA-1 sum returns a different string. It's a longer string because it's 160-bit base versus 128-bit. A which of SHA-1 sum shows that it's in user bin, and an RPM query file of the output using backticks tells us it's a member of core utils. Let's just take this command we've just executed to quickly explain what it means, since we have yet to talk about this shell feature. Note, backticks are used to support shell-based command substitution, which is what we've just executed. So for example, this causes the output of which SHA-1 sum, which we know to be a path user sbin SHA-1SUM to be submitted to the input stream of RPM query files. It's a way of taking the output of a program and substituting it on the command line real time for the process that's executing. There are two ways to do it, one using backticks and another using $ and parentheses. So for example, RPM query file, $ parentheses, close this out, parentheses, would achieve the same result. So let's just note, or RPM query file, $ open parentheses, which SHA-1SUM achieves the same effect. In scripts, you'll often see this notation, but backticks also works. The backtick command is located left of your number 1 key, so in the upper left section of your English-based keyboard. So SHA-1SUM also belongs to core utils. So let's take a look at our 1 million files. LSL 1 million star, SHA-1SUM 1 million star, and this will generate sums for all of them. Let's see where the differences are. Notice that these files here are all the same, and then when we get to 5, because we varied it, it changes. Ditto for 6. And then of course there are unique sums for the BZ2, gzip, and zip files as expected, because they are different, because they've been encoded with different binary sets for their respective applications. So those are the SHA-1SUMs. Now, what if we wanted to generate a list of sums and share them in one document? Well, we could use output redirection. So for example, we have a list of files that we'd like to share with a recipient. So we would SHA-1SUM, let's say 1 million star. This will generate a list of sums. In conjunction, and that's backticks, we want to get rid of that to avoid confusion. And in conjunction with output redirection, we could create perhaps a file named SHA-1SUMs, or perhaps 1 million.text.SHA-1SUMs to indicate that these sums are within one file, or the various files' sums are contained within. This will generate a file with all of the sums as we've just seen on standard out. And then the recipient can use the SHA-1SUM utility to check wholesale all of the sums. So as opposed to dumping the SHA-1SUMs and standard out, we send them to a file naming it 1million.text.SHA-1SUMs. When we lsltr 1 million star, we now see a file that's 511 bytes, and if we cat its contents, SHA-1SUMs, we'll see that it includes the sums. So if you share this file along with the source files with your recipient or your business partner, they can then wholesale confirm that each of the received files match the sums that are reflected within the sums file or the text summary file. So see SHA-1SUM, and if we check the sums, 1million.text.SHA-1SUMs with nothing else, then for each line the sum will be matched or attempt to be compared against the file that's referenced on the same line. So this sum will be compared to 1million.text, this sum will be compared to 1million.text5, and so on. So let's try to confirm the sums. So let's just note, confirm sums, and better yet, SHA-1SUMs wholesale. And this will do it on the fly for us, which means it'll run the sums on the fly, and it returns whether or not the sums are okay. Now if we alter the sums at all, an error will be generated. Let's modify star SHA-1SUMs and use tab completion. Let's change 1million.text.zip, since it's the last one. Instead of to 2, let's make it 3. That alone is enough to generate a useful difference for SHA-1SUM to be able to detect. And notice that 1million.text.zip failed. Warning, one of the 9 computed checksums did not match. So if you send a batch of files to a business partner, they could wholesale check the sums, whether it's MD5, SHA-1, 256, or 512, and determine, perhaps programmatically, whether or not there are any discrepancies. Now let's fix the discrepancy. Another way you can run a command that was recently run in your history is to simply use the exclamation mark followed by the unique characters from the command, such as NAN or NA. That runs the most recently executed instance of the command that's in memory, or in the history, that is. Now let's change 3 to 2, and then rerun SHA-1sums, and it works out. Now what if we modify this file? What if we introduce an additional space, let's say here, for example. Let's see how it behaves. And it sees that the file has a leading space as a file name, so it doesn't work. Let's reset it. It needs to be orderly, and now it works. So you can wholesale check sums to see whether or not things are intact with SHA-1sum. The same applies to MD5 and the rest. So let's look at SHA-256sum, which uses 256 bits for generating its checksums, which means it is more secure and harder to break. Let's just note that SHA-1sum uses 160 bits, and we've noted that up top, so no need to renote it. But since the context will shift momentarily, we'll leave that one in place. So SHA-256 sum, and we can list a set of files, 1 million star. We'll generate those files and we'll send it to 1million.text.sha256 sums. So this will create sums based on 256 bits. Again, if you have a lot of files that you're dealing with, this is exactly what you do. It's just pipe them all in, generate them all on the fly, and store them in a file. Just like that, it's been generated because the files are small. That's LSLTR 1 million star, and there we see the 256 sums file is considerably bigger, as expected, roughly 60% bigger. Let's cat the contents of 1million.text SHA-256, and there are the longer strings. So we expect it to be longer. We can always add a little space horizontally by stretching this window out a bit, and this will allow us to fit everything into a nice page. So now these are the longer 256-bit base sums. To confirm them wholesale, run SHA-256 sum. You can run the help option to see the available options. Check is the C option. Text mode is default. There's no difference between text and binary on GNU systems, so this can be ignored. We can run in quiet mode where OK is not printed for each. We'll try that momentarily. Let's do a SHA-256 sum check against 1 million text SHA-256, and this will return OK for each. But if we introduce the quiet option, then it suppresses the output, which is useful in scripted environments. And then you'd simply echo the exit status, and if it's 0, then you know that all of the sums have checked. If it's non-zero, then one or more of the sums failed. So for example, let's modify 1 million text SHA-256 sums. Let's change one of the sums. Let's take this sum. Let's make the leading character B instead of A. And then let's rerun SHA-256 sum in quiet mode against it. And notice that it tells us that one of them has failed. And it's the one that we just changed. So one of the 10 failed. And if we echo the exit status, it's non-zero. Now let's fix the problem. Changing this to A. And let's see if we're able to get out of trouble here. If we've gotten the right one, and we don't have the right one, so we've changed two of them incorrectly. So this perhaps is B, and this is perhaps A. Let's see if we've got it right this time. In fact, it tells us the file. It's 1million.text.SHA-sums. So let's see what happens this time. And this time it ran successfully. Excellent. So the quiet mode is useful in a scripted environment if you'd like to suppress the output, because it's not considered to be important for your execution. Let's just note that it's an optional way of executing it. So SHA-256 sum, quiet, check, text.SHA-256 sums, quietly checks all sums. And let's just note, returns error if one or more fail. One or more checksums, of course, fail. And then the last one, which is becoming more prevalent, which you should consider using for generating longer strings, is SHA-512. Now, it's not available on all systems, but if you're running Red Hat Enterprise 6, you'll have access to it. And if you're running an older system, you can download either source or binary for SHA-512. So the syntax is similar. SHA-512 sum for consistency, 1,000,000 star, sending it to 1,000,000.text.SHA-512 sums. This generates the sums, and then we follow this up with a check momentarily. So let's see what's happening here. And we'll echo the exit status once this is completed. We can begin typing, by the way. And it's ostensibly ready, so there we see that it's even bigger. Now it's roughly 50% bigger, so we went from roughly 60%, or actually roughly 100% bigger, so from 60% differential to 100% differential because of the size of the checksums. Now let's cat the contents of 1,000,000 text SHA-512, and you'll see that the strings won't fit within our screen. So even if we stretch it out even more, we'd need much greater resolution, but that's besides the point. We can always check the sums. You can also always check the number of sums that are within the file by piping the output to WC, the word count utility with the L option turned on or enabled to count the lines. There are 11 sums. Now let's see how many text files are here. And we should see it reflects, of course, 12 because we've got some other items in there, but nonetheless 11 sums were generated for raw text files and for the gzip and so on. So 12 makes sense because of the additional file. So when we generated the 512 sums file, there were 11 files including the sums file, and then at the end of the process the 512 sums file became the 12th file. So let's recat the 512 sums file again, and you'll see all of the various files. At the time that this file was generated, SHA-512 sums did not exist. It now exists. If we regenerate it, for example, let's look for SHA-512 sum, dumping it to the same file, and then recatting the contents. We see it now includes SHA-512 sums. So now these can all be checked. So let's SHA-512 sum check, 1,000,000 text SHA-512 sums, and this will check all of the files and tell us whether or not their sums are okay. We expected this one to fail because it changed during generation. So this is expected because, again, during the generation the file changed. Its content actually changed. So that's to be expected. So that's just one caveat, that if a file's changing while you're summing it, that's a problem. Note, if file changes during checksum calculation, then its checksum will be incorrect, resulting in confirmation failures, which we see in our case, which behooves us to remove the entry. So let's modify the file, 1,000,000 text SHA-512 sums, and let's remove the entry that contains. We can just search a document for 512 sum, and it's the second or penultimate line. And now let's recalculate to see if the 11 check, and they will. So they're all okay. This looks good. The exit status is clean, whereas before it wasn't clean. So as a quick recap, we have a number of tools: MD5 sum, SHA-1 sum, SHA-224 sum, which we've glossed over, 256, and 512. You can search for them using which. For example, which SHA-512 sum, and you should use SHA-512 wherever possible. If your business partners don't support it, also generate a set of perhaps MD5 sums, 128-bit, or SHA-1 sums, which most organizations should have some sort of support for, even if the environment, the target environment differs. Let's say if they're running Windows, for example. There's definitely support out there for SHA-1 and MD5, and 256 and 512 is available, but not all environments have it currently available. For example, the newer Linux distros like Debian 5X, Red Hat Enterprise 6, SUSE Enterprise 11, Ubuntu all support these checksum algorithms. And it's a great way for you to determine whether or not content has changed during transit, whether within your environment or outside of your environment, because data are likely to be changed either purposefully or inadvertently. So something to keep in mind, work with your sums. When you see sums online, like even on our own website for ISO images, if and when you download those ISO images, run them through one of the checksum algorithms or mechanisms that are reflected on the website to determine whether or not the content's legit or has been changed or not changed or so on. There are times, however, you'll find checksums online that don't match checksums of content downloaded because of the failure to update the websites, for example. And we're guilty of it sometimes with the appropriate checksum information. So sometimes documents are updated, like web pages are updated with incorrect checksum information, but the checksums that check on the client side happen to be correct. So those scenarios will occur, and you'll just have to work around them. But nonetheless, you have a mechanism for determining whether or not bits have changed in the document in terms of the order in which the bits are arranged.